Good afternoon, everyone. Today we are starting for the live session 4 of the course named as Optical Fiber Sensor. So today we will discuss little bit about the brief um, uh, talk about week 4 of the course and few questions related to that. Um, let's move to the slide. Yeah. So we'll start from the first thing, which is the noise, which is the main problem while we are detecting any signal. So previously in a last session we have discussed about what kind of noises are there and how to mitigate them, but to mitigate that we need to use multiple things which we'll discuss today. So first thing is the noise is having the random arrival of, because of the random arrival of photons, or it can be because of the thermal activation, dark current. Also it can be possible because of the many factors. So today we'll discuss about the how we can increase the signal to noise ratio, and what are the things we need to we need to deal with that regarding the to reduce the noise. For that, first thing is accumulation, as I discussed in the last session, that reducing to reduce the noise we can use accumulation. Just a second, somebody is about to join. Yeah. So here we can see that how the noise can be reduced. For that, first thing is given here, that the histogram for this noise pattern. This is the noise which is looking at the x-axis is time, and the y-axis is output signal, and this histogram shows that how much number of points are here in this during the time. So you can see that Vs of this is this red arrow mark, and the variation we can say in the noise variance we can write as a sigma square. So to reduce that, what we can do is we need to do one full scanning and collection, and the second one also it can be same like that. So if you do this, what will happen is it will there was a equation which to reduce the noise, and the SNR will reduce if you are doing the number of accumulation n times. So it will become it will become root of n, under square of n. So under root of n, so how we can write the SNR of the full scanning, like n number time collection, will be n SNR, n is equal to 1. Okay, so suppose you are doing 100 times of n collection, so this root 100 means 10, so SNR will increase by the factor of 10. You can see in this how it is increasing. The first single shot noise, there is like signal is quite noisy, and once the averaging of 10 has been done, and it is noise is reduced drastically from this much to this much, and once it is done up to 100 of times accumulation, then it is almost like a crisp and clean square wave. Similarly, there will be a problem with the bandwidth. If you are increasing, if you are doing the averaging, so it will also, it's a low pass filter kind of averaging, so it is acting as a low pass filter, and if you are increasing the n, it will obviously have the high precision, but Also it will reduce the bandwidth. As you can see in the timing, if you can see the time scale, then it will be bandwidth will decrease so much drastically. Then moving towards the next thing is yeah, so there will be like how many times types of noise averaging we can do. So best is the Savitsky-Golay fit. That is one of the best thing, where what it does is, suppose you have points, number of points per time. Suppose voltage will take, so, or amplitude we can take better. If you see in this particular fit, what will happen is, we'll take some 5 to 10 points, 5 to 10 points, suppose 5 to 6 points, suppose, and we'll average it with that. So this 5 points will be averaged and averaged out, and it will make us like it will be noisy. So if you average it, so it will become like this, something like this. Okay, and for next one, to go for the next collection, this fit will be increased by factor of 1. So again 5, this one will this 1 point will not take, and will the previous point, we 1 by 1 will decrease. So suppose previous points 10 were there, so 1 point will 1 to 10, so first point will remove from the during the feed, and will start from the 2 to 11. Like that if you do, then it will be average out, and you will get lesser noise. And if you see what I can say, if you see suppose you have one kind of square wave, and you want to reproduce during the detection, so it will look like this. Suppose you are starting from the noises are there while collection. During the detection, it will be having, suppose you are taking 10 points, so 10 points, what it will do, suppose from here to here it is having 10 points. I'll just change the color of pen. Okay, suppose here to here it is having 10 points. So what it does is, during the averaging, it will take the noise level, the baseline, like this. It's not correct actually, something like this, yeah. So it is not like a square wave, whatever we want. So what we need to do is, we need to take lesser n, 3 to 4. So the points, if you are taking less, then it will be averaging, and it will become like this. You will get something this way. Okay, so averaging out, it will almost have some if you are reducing the numbers, then it will increase your the probability of getting the square wave properly. But there are also some issues are there. If you are doing this one, you will not get the SNR, high SNR. So number n, the factor n, yeah, so factor n, if you are decreasing 3 to 4, then SNR also will not improve much. But if you are increasing SNR based on this n is equal to 10, then you will be having problem with the getting the proper square wave. So that's the problem. Okay. Yeah, moving towards the next thing, that is the um, lock-in detection. So in lock-in detection, what it does is, like, you will be having the noisy signal and the reference frequency, both will be mixed, and you will get the multiplication move signal to DC noise, where it is having the multiplication, and after that it will go to the low pass filter, where you will get the proper DC voltage clean. So here the amplitude is proportional to the signal amplitude. Okay. Then moving towards the next thing, that quadrant lock-in detection, where there will be a cos and sine mixing will happen. You can see here the cos omega t and sine omega t 90 degrees shifted, and both will filter from the low pass filter, and recombination, after recombination you will get the proper signal, reducing the noise. And the magnitude will be r is equal to under root x square plus y square, and phase will be tan of x y by x. Okay. So this week was fully for the gas sensing and signal recovery. So first thing is, like, I'll discuss about the gas sensing, where the usually the optics, which is IR radiation, electromagnetic radiation, are visible, and these radiations can directly interact with the gas molecule, and can be absorbed to have some kind of interaction with the electromagnetic radiation. So first thing is, with the IR, what happens is, you have heard about, I think you have heard about the FTIR, where the gas will be having some kind of atoms will be having vibrational, rotational, and translational, those kind of uh, activities when it interacts with the infrared radiation. That's why this FTIR instruments comes into the picture. And one of the main thing is there will be a functional group region and the fingerprint region. So gases usually have nice frequency fingerprint regions, absorption, and it is generating some kind of vibranic, um, uh, stretching, bending kind of activities in the molecule, and that's why the absorption can be seen nicely if you are detecting it. And the second thing is the visible light. It also interacts with the gas molecules and absorbs, and might be emitting, can be as an emission, or it can be also the Raman spectrum also we can get. So elastic and inelastic collision also can be happen with the gaseous molecule. Also it can absorb the light and excite to the a higher energy state and electronic state, and it can also emit from there. So for that, it should be usually it should be visible UV light. So the physics behind this sensing and signal recovery is, for the gas sensing application, is light matter interaction and the quantum mechanics of the absorption, that we need to think about before going to the absorption region, absorption of the gas, and for the gas sensing application. Then there are challenges also, that deploying sensitivity optics in harsh and high dust industrial stacks. Then the solution comes with the gas sensing, um, uh, non-destructive gas sensing method. So one of the best method is optical gas sensing, where this lock-in and quadrant detection can be useful. Um, the baseline and amplitude modulation signals can also we need to discuss about it. So first thing is the amplitude modulation sensor, how it works. So in a macro scale we see that the line of sight blocking, and micro scales we see that the molecules are absorbing. So you can see here that intensity versus time, if you are plotting, so we'll get the blockage of light if you are keeping something the obstacle. While if you are seeing that the molecules are absorbing, so what will happen is, like, it's in an environment where the suppose carbon dioxide concentration is quite high, or tiny amount of carbon dioxide is there. So the source, like a laser source, monochromatic laser source, will be aligned in such a way that it will be um, the light is propagating and receiving by the detector, and during that the dioxide molecules can also interact with the light and can absorb it. Suppose you are saying that IR, infrared light, so it will absorb some amount of radiation wavelength, and that's why we will get the absorption dip there. And the IR will be having some kind of transmittance versus um, wave number plots, and there we can see that how the dip is happening, where we are exciting where the CO2 is absorbing. So one of the, like this, you can see this kind of absorption, sharp absorption will happen, sometimes broader, but not in the CO2 or any other gases, mostly in the sharp. So there will be in IR, it will be having just to tell you that in a fingerprint region it will be 400 to 1500 something, and there from there onwards it will be having up to 4000 wave number. It will be having the functional group region. This is the fingerprint region, and this is functional group region. Functional group region means if you have some kind of molecule, suppose benzene, will be having the functional group also, suppose nitrobenzene, so NO2 on top of it attached with the benzene. So this is a functional group, so it will be having some kind of functional group absorption also. So it will come this side 1500, above 1500. Similarly, here it is mentioned about the basic plot, intensity versus time, where you can see that the signal, how the lights are absorbed at the moment, like time, the intensity is decreasing because the light is absorbed by the gas molecule, and based on that it can be sensed that how much light intensity has been reduced when once it is interacting with the gas molecule, and how much is transmitting to the receiver if this particular time interval there is no absorption, and it seems that there is no gas molecule interacted with the laser light. But here in this particular region, there were some interactions with the gas molecule. So the physics of the absorption spectroscopy, just now I have told you already, but in atomic scale or in a molecular scale, what is happening? So if you are talking about the infrared spectroscopy, so there it comes in the picture that it will absorb and it will be having some kind of vibronic interactions. So but if you are talking about the electronic, then there will be a quantum jump. So you can see here that one light one photon of energy E is interacting with the one electron of the atom, and that is exciting that lower energy electrons, and uh, this electron is moving to the excited state, and that's how this absorption of photon is happening with the energy gap. It is a quantized energy gap. Similarly, you can see here that why this broadening happens actually. Why when once we are collecting the spectrum and seeing that, um, if you are collecting the spectrum with the time interval t and intensity, so what happens, like few of the molecules are interacting when the light hits one molecule, and second time it is not interacting anything, so light is propagating towards the receiver. Again, two gas molecules are interacting, and it is also going there, receiving by the detector. So you can see that the absorption first time it will be having some dip. So as you know that the molecules, diatomic molecules or triatomic molecules, should have sharp dip. Similarly, for this condition, for another condition there is no absorption, because there was no interaction with the atom. There was no interaction with the gaseous molecule or molecular atom of the gas, and you can see here once two were there, so it will be having little bit more dip compared to the previous one. But why the broadening is happening? So the broadening reason is the Doppler broadening, we are saying that. So once the resonance wavelength in the middle will be having some kind of collisions, multiple collisions, and that's why this Doppler and collision broadening comes into the picture. Moving towards the next thing, that is Beer-Lambert law, which is very much famous for the absorption in spectroscopy, where the input light's intensity lambda, it's mentioned, so you can take the lambda in UV region something like 350, 400 something, and the output lambda. So what is happening, like molecules are absorbing the light, and that light, first thing is that is absorbing, second thing is scattering is also possible, but whatever the light is absorbed, and after that the remaining light moving to the detector. Suppose here is the detector and this is the light, laser, I'll write, or for this case maybe I'll write the lamp, which is having the particular specific wavelength light is coming into the interacting with the gas in a chamber, and the path length also mentioned here, how much path length it should be, to understand how much we can quantify based on the path length how much absorption should happen with the concentration of the gas. So the number of number or concentration we can keep, and path length, if reducing the path length, then absorption also will be reduced, increasing it will increase more, and then this is the probability, transition cross section probability, okay, which we have discussed previously in this here spectrum. Okay, so moving towards the next thing, I hope you have understand this, what is happening here. The absorption, after absorption, the collection, after absorption the intensity will be reduced drastically based on the path length and then the concentration of the gas or any other solution or solution state or gaseous state we can um, quantify. So this is the Beer-Lambert law. Apart from that Beer-Lambert law, one more thing is that if you want to sense the solid state, which is not applicable here in the sensing application, so what will happen, like you have solution state film that can also be absorb light, but we will not be having the uh, mostly the solid state films or powder will not be having any um, um, transmission geometry, like we can't keep in a transmission geometry because it will absorb and block the light. So we will be having the reflection geometry. This is how it will reflect the light. So based on the reflection, that is a different thing, different story, which is not applicable here for a while. But I just wanted to say that this constant n number of the atoms, you can say that concentration also we can keep. Then gas and solution can be measured with the Beer-Lambert law, absorption efficiency. Then moving towards the industrial application. So as you know that so many industries which are using the for the chemicals or any like drug manufacturing, where there will be various gases they will use, like ammonia, nitrous oxide, then sulfur dioxide, carbon monoxide, carbon dioxide. It also release uh, very toxic gases along with the chemical production. So those things they need to maintain in such a category that uh, the concentration that in a ppm level or um, even below that um, ppm level, so that it should not be harmful for the environment, and that can be used, that comes into picture. And uh, there optical uh, this sensors, optical gas sensors, gas detection can come into the picture and help us in the to monitor that live. So the company should not have violated any rules live detection. Okay. So context is that there will be a coal fire plant operated at extreme temperature with high dust load and vibration. Then there will be a regulatory target, like sulfur dioxide should not exceed the limit, nitrogen, monoxide, dioxide, those things, and ammonia. So you can see that the CB standard, which comes into the picture to monitor this gas concentration or gas um, level, should not exceed. So where that critical risk is excess, ammonia injection reacts with the sulfur from aluminum bisulfate and a hard solid that clog plant infrastructure if not monitored at less than 2 ppm precision. So you can see that how it is a serious thing, need to be monitored properly, and where this gas light to gas detection comes into the picture. First thing, this is the measurement architectures where first the cross duct in situ measurement can be done like this, where uh, laser, suppose here it mentioned the red laser, will be having one side uh, situated to the plant, and there will be one window, and another window is for the detector is kept there, and this is the length of the um, uh, your chamber, um, reaction chamber. And as we discussed just now, that Beer-Lambert law, the L length also um, we discussed, yeah. So length also plays a role to absorb absorption of to check the absorption, how much efficiency is coming. If you increase the length, the absorption will increase, and then if you're decreasing, then absorption will decrease. Similarly, concentration, but concentration we need to measure here. So length is fixed, and the concentration we are measuring based on the everything we are keeping constant. Input laser intensity of the particular wavelength, and detector also is detecting, and based on that the concentration can be in situ concentration detection can be done for using this light based sensor for the gas chamber, for any industry which is suitable for this kind of thing. Then in situ probe, where there will be a probe need to be inserted into the chamber of the reaction, and this filter will, which is 2 to 20 micron filter, will collect the gases, and which can be detected. Okay, so what is the problem with this and this is why we need to go for this one, cross duct one, because the in situ probe measurement requires very heavy installation, like more than hundreds of kgs of instruments you need to apparatus you need to install in the chamber to measure those kind of gas concentration or concentration level. Moving towards the extractive, this is the another method where this there will be one pipe which is connected with the a separate chamber, where all the measurements and analysis will be done using those the gas which is released in the chamber. And again it is having the problem with the installation and more expensive. So one of the best is the optical gas detection system. Then there will be a few things which you need to understand. First thing is like differential absorption spectroscopy, which is called DAS, where the intensity and wavelength when the absorption is happening. So as we discussed line broadening and the Beer-Lambert law and then Doppler effect, so that's why this broadening is happening. And you can see here, from here, non-resonant absorption by dust is reducing this much intensity, and after that the gas and dust will absorb again up to this much. Okay, so how we get to know that the gas is absorbing or it's blocking by the dust? So we'll be having some kind of ratio. So external losses we can calculate n external, which is equal to -1 by sigma L ln I intensity of the lambda r, and r means the resonant, and intensity of the lambda nr. So you can it can be easily understand that how much intensity is reduced because of the gas. moving towards the hardware selectivity. So there will be um, if you see about the gas filter correlation GFC, where that um, first thing will be the in that system will be broadening IR lamp, then reference cell where the rotating GFC wheel will be there, and based on that the it will the filtered light will propagate through the chamber, and after that this will be detected another side of the chamber. So this gas filter correlation is very useful to detect various gases separately, like NOx or SOx. Meanwhile, it can be detect also ammonia. So based on that, we need different GFC wheel, like the chamber in the GFC wheel. Then let's yeah. So wavelength modulation spectroscopy also we need to discuss little bit, where the laser diode module and absorption profile. After absorption profile, it will be extracted in the 2F. So from the input to interaction to output, it should be measured properly, and to detect it there will be a second harmonic 2F we should detect, which is better than better correlation for the gas detection compared to the absorption profile, where the dust also will be dust particle which is blocking the light also can be play a role. Okay, so the 2F signal is sensitive only to the curvature of the absorption line, and it completely ignores flat background absorption like dust or linear noise slope. So that's why we need to remove this part which can be potentially because of the dust particle. Then the next thing is fiber optic frontiers, where there will be a tapered fiber. The optical signal or wave um, so um, your input laser light will be propagated through this glass fiber, which is the tapered at one place, at this place, and these molecules are interacting, gas molecules are interacting with this tapered area, and because of the absorption why it is interacting, because it is having the evanescent field. Once it is propagating through the optical fiber, it's also absorbing the molecules are absorbing because of the evanescent field once it is coming into the near field region, and because of that we we will get the spectra where the absorbed signal we can see easily. So this is one of the optical sensing application using this tapered fiber, which is well known nowadays. And another thing is the whispering gallery mode, where the light is propagating in the cavity, and this cavity will be having the circular light propagation. You can see here like this, and because of that there will be constructive and destructive interference, and we'll get the optical modes, and those optical modes will be having very high Q factor if you are using the proper cavity. And this cavity, if the molecules are interacting with the cavity, will be having some kind of interference, and that's how this detects the absorption of the light, and based on the concentration of the gaseous molecule. So for today, we will finish this like end of the discussion. Now we'll move to the question and answer session. Please let me know if you are understand if you understood all the things. If you have any doubts, let me know. Were you able to understood? Yeah, please. Your voice is not coming. Can you say louder, Janani? I don't know, it is not coming. Just a second. Yeah, now please tell me. Problem is there. I'm not able to hear you. Are you able to hear me? Just type in chat box. Am I audible? Yeah, okay. Yeah, so if you have any doubts, you can ask in chat box also. Just give me 5 minutes. I'll have water and we'll continue with the question answer session. There are so many interesting questions. We can also go through it. Okay. Okay, let's move to the question answer session then. If you need to cooperate, you need to discuss about more and more. Okay, I'll ask you questions. Based on that, you need to give your answers. Okay. So first question is, in the context of optical sensors, why is an amplitude modulated, intensity modulated means sensor generally easier to construct than polarization or phase modulated sensors? First option is, the source radiation does not need to be expressed in terms of an electromagnetic wave for intensity measurements. Second option is, the optical receiver can directly detect changes in power without requiring a preceding demodulator. Um, Third option is, intensity sensors are immune to external perturbations and background noise baggage. And the last option is, amplitude modulation requires significantly less power from the optical source compared to frequency modulation. Can you provide your answer? Both of you? Others are looking on the YouTube, not joining properly. Please let me know your answer. Try to answer, guys. It's quite easy. Have you understood the concepts, or you have still doubt on the concepts? Um, Anyone, please tell. So here, what is happening? We are discussing about the context of amplitude modulated sensor. So usually, amplitude modulated sensors, first thing is, it doesn't depends on the wavelength. So uh, only the intensity. So intensity can be, the optical receiver can directly detect changes in power without requiring a preceding demodulator. So we don't need any kind of demodulator for this. Just optical power which is changing can change the amplitude modulation, and can sense the amplitude modulated signal. So um, there are four options. First option says that source radiation does not need to be expressed in terms of an electromagnetic wave for intensity measurement. It should be mentioned as expressed as an electromagnetic wave. Otherwise, how it will have the modulation, the sensing. Then intensity sensor are immune to external perturbation and background noise package. So that is not required. Why we need intensity sensors are immune to external perturbation? External perturbation and background noise package is for the absorption, not for the amplitude modulation sensor. So the last option is amplitude modulation requires significantly less power for the optical source compared to frequency modulation. It is not correct, because it doesn't depend on the power. It might be it should be more than that, because we are playing with the intensity should be higher or lower or zero, something like this. So it can be played like this. So one of the best, the convincing answer is this option B, which is the optical receiver can directly detect changes in power without requiring a preceding demodulator. Okay, moving towards the next question, which we have discussed in the discussion slide also. According to the BA-Lambert law, what is the mathematical relationship between the transmitted intensity IS and the incident intensity I naught in a gas cell? Let me know which one is the correct one. IS and IL is mentioned here, and there is a relation between them. Please text in chat box also. It is useful. It can be useful for discussion. If you don't want to, I don't know why your voice is not coming, so you can type in chat box also. We have 10 more questions, 8 more questions after this. Total 10 questions. One by one we'll discuss, and after that we'll move for the next week discussion. Next week. Guys, type in chat box at least. So the correct answer is, need to discuss. So the source intensity and the incident intensity, it depends on the path length L and number of concentration, number of gas molecules. So concentration also we can say, or volume. So N by V, or because we are discussing about in 2D, so for a while we'll just consider the N, which is interacting with the gaseous molecule. So from this side the input light is given, and after absorption the output is coming from this side. Okay, H nu 2, H nu 1. It will not be 2 actually, it will be 1 only. After absorption it will be with the time interval it will be having the dip because of the absorption. So as you can see that the source light, the uh, the transmitted intensity IS IS actually IS is proportional to input intensity. Obviously it will be, because that's what the laser source is hitting to the sample and transmitting uh, through that cavity cuvette. Then what is the relation with the concentration and length? Both the transmitted intensity is also proportional to the exponentially decaying with the length. If you are increasing the length, exponentially the intensity will decrease, light intensity, and absorption will increase more because number of collision will increase more. Similarly, this also uh, exponentially decreases with number of molecules or concentration, you can say C also you can write. So these three are there, and one, if we multiply it and we'll keep it in the final equation, so it will become I naught E minus sigma. Sigma is the constant here, okay, like an epsilon, how we are keeping epsilon. So this is a sigma here. So this is the correct correlation with the between the relationship between the intensity and transmitted intensity and the incident intensity. I naught IS. Did you understood, guys? Did you understand? Moving to the next question. What is the primary purpose of taking a second measurement at a non-resonant wavelength in differential absorption spectroscopy? So there are options, which says, first option says, A says, to identify and cancel out uncertainties caused by external losses like scattering or interference reflections, to compensate for the Doppler broadening that occurs at the resonant wavelength, and third one, C, to double the number of photons reaching the detector to improve the signal to noise ratio, and D, to increase the effective interaction length of the gas cell without physical modifications. Please let me know your answer. Today Janani is not discussing. What happened? John, please provide your answer in chat box or directly also you can tell. Okay, so as we discuss about the non-resonant wavelength, which is coming when the absorption is happening and some kind of slopy region is there before the proper absorption, and that floppy region, because of the interaction with the dust particle and other reflection or scattering intensity, because of the reflection or scattering, so you must be having like this something. So this region and this region, because of that, this non-resonant wavelength has um, in a differential absorption spectroscopy. So what is the correct answer here? First option, to identify and cancel out uncertainty because of external losses like scattering and interference reflection. Second is to compensate for the Doppler broadening that occurs at the resonant wavelength. That is not correct, which is not even relevant with the non-resonant wavelengths. Third option is to double the number of photon reaching the detector to improve the signal to noise ratio. It can't do anything. We need to use some kind of op-amp or the detector, which is APD, avalanche photodiode. We can't use non-resonant wavelength to double the photons. Then to increase the effective interaction length of the gas shell without physical modification, which is also not relevant with this particular phenomena, because that again there is no relation between the length, or it's a constant for the detection, and that's how the correct option is option A, where because of the scattering or interference reflection it is happening. Moving towards the next question, to achieve trust level detection of gases in part per billion, which two factors should ideally be maximized according to the principles discussed? Option A, source bandwidth and receiver temperature. Option B, absorption cross section and interaction length. Option C, current tuning range and detector surface area. And D is number density and collision broadening. Please let me know your answer. Jenny, your voice is not, it's not coming actually. You can type, I think, better. I don't know what happened suddenly. This is phone. Option B. Option B. Huh? What about John? What's the option?
Sir, A.
A. Okay. So, yeah. No, actually, option A says that source bandwidth and the receiver temperature. Before that, we need to move for the absorption efficiency, no? So
Yes.
its receiver temperature and the source bandwidth will be constant for um, the whole apparatus, whole instrument. So it will be maintained at a certain temperature. So the correct option will be option B only, where you will be having the absorption cross section and the interaction length, which comes into the picture. to to detect the stress level like a part per billion. If you increase the L interaction length, then it will not be that much efficient to detect up to ppb. Okay, understood?
Yes.
Okay, so Janani is correct here. um, so the next question is, can you just mute your mic? Yeah, please. If an optical sensor performs an independent measurements and averages them, by the by what factor is the signal to noise ratio SNR expected to improve? Please, both of you give your answer. We have discussed these things also. John, please. Option A. Janini, option A. John, your answer.
So B log N.
No, no. I think your concepts, you need to recall it. We have discussed in the starting itself. Listen carefully. This one. See, the SNR improves by the factor of under root n.
Yes.
So, if you want to reduce, if you want to increase the noise ratio, signal to noise ratio, um, you need to
Yes.
multiply it under root n. Okay.
Yes, sir.
So if you are taking 100 times of average, your number of times, 100 number of times you are averaging, so you will get 10 times SNR. Okay, so n is equal to 1. So if you are getting signal to noise ratio something like 100 for
Yes.
example, so n, if you are keeping 100, then you will get the signal to noise ratio 100.
Yes.
Okay, under root n. And if you are getting if you are keeping n is equal, if you are accumulating n is equal to 10 uh, 10,000 times, so SNR will be 1000. But you are accumulating, but that is not a good thing. You will get very nice square wave clean crisp and clean data, but there will be problem with the bandwidth. Speed will reduce drastically. Detection speed also matters. So we need to play with the both. The SNR also we need to uh, take care, and along with the bandwidth also. So detection should be very fast. So the correct option is option A, under root n.
Yes.
Log n is not the correct one. Okay, and other things not at all. So just recall it for your concept. Okay. Okay. So moving towards the next question, what is a significant disadvantage of using a large window size and for run length averaging in a sensor system measuring fast varying signals? So option A is it shifts the mean of the Gaussian random variable away from the true signal value. Option B, it prevents the detector from reaching the thermal noise limit. Option C, it increases the standard deviation of the noise samples. And the last one is it smoothens out transitions, thereby reducing the effective measurement bandwidth. Let me know your answer, guys. Chanani, most of the times you are correct. Both the questions you have given answer correct. Option D. Okay, what about John? Please give your answer. Yeah. Anything? Okay. Um, John, anything you want to say? Any option you can select. So this time also Janani is correct. So what is happening here is um, large windows size, and suppose you have a square view nicely, you are giving input, and while transmitting it might lose some of the like, because of noise mostly the detection is a very weak signal. If you are detecting very weak signal, so what will happen, we need to average it out to reduce the noise. Okay, you can see here that how the random arrival of photons are hitting to the detector and generating the various intensity. Some are going very high, some are going very low. Now we need to average it out. So what we need to take is run length averaging, and run length averaging says that n we need to keep something like um, uh, we have discussed about the histogram where we saw that how the Gaussian signal variance shows that Vs. Okay, so if you have so much density in this area during the noise also, some are there here, and but most of the points are in the center of the this Gaussian variance. You can see once we are averaging out 10 points, so it will smoothen the data and you will get something like this. Okay, it's not like this maybe, yeah. So it's not perfect square wave, it is like it's not having the edges, sharp edges, and that's what it happens when we are doing the run length averaging. So this is the significant disadvantages when we are doing the large window size, like the n is very high for the run length averaging. So what we need to do, as we discussed previously, and let's go through the slide. Yeah, so to average it, this is the best method, Savsky Gole fit. Okay, so you doing the run length averaging better than this is the best. Okay, where what will happen, first data points 1 to 10, that will be chopped into, suppose you have 1 to 100 data points, from here 1 to 100 it will be chopped small chunks like 1 to 5, 2 to 6, 3 to 7, 4 to 8, and those after averaging will get the proper signal information, intensity information, or you can say amplitude information, which will be look like this. Not perfect square wave, but information will be intact, much more better than the previous one. Okay, like this something. So this is correct answer. Now moving towards the next question. In the context of industrial emission monitoring, what is the selective catalytic reactor, CSR, used for? So we discuss about this also. First thing is removing sulfur dioxide by spraying lime into the exhaust gas stream. Second, measuring the calorific value of coal before it is pulverized for combustion. Third one is reducing nitrogen oxides, like there will be NOx, by reacting them with injected ammonia to form nitrogen and water. And the last option is filtering out fly ash and charged dust particles using electric plates. Let me know your answer. Channi, John. Have you read about this one? SCR, selective catalytic reactor. It's mostly the, it's not like optics related thing, but just to understand that what is happening in the chamber, why we have ammonia concentration we need to maintain, and need to monitor the nitrogen oxides concentration. So there will be this option correct. Okay, why I wrote this question is because this nitrogen oxides need to be, it's very harmful, and we need to reduce the concentration drastically to ppm level. For that, in the chamber we need to inject ammonia, and ammonia will react with this nitrogen oxide and form nitrogen and water. And this reactive nitrogen oxides, these reactive nitrogen oxides will be converted into harmless nitrogen and water. Next question is, why is it critical to maintain high temperatures, typically above 220 degrees centigrade, in ammonia sensors used in industrial stacks? To prevent the formation of solid ammonium bisulfate, which can clog the instrument base, to ensure the semiconductor laser stay within its current tuning range. C, to increase the Doppler broadening to a level that the spectrometer can resolve. D, because the absorption cross section of ammonia is only detectable at extreme heat. Please answer. So the correct answer is option A. Why it is correct? Because none of the other optic related parts are correlating with the temperature. Temperature can be should be constant, but not typically that range we need to maintain for the detection or Doppler broadening. We don't need this Doppler broadening here. Okay. If it is sharp, then it's better. Doppler broadening is also not good for the detection, spectrometer detection, but some extent it should be. Then there is no relation with the absorption cross section of ammonia, which is detectable at extreme heat. It's not like that. Also, it is not related to semiconductor laser should stay in that range. So the correct option is to prevent the formation of solid ammonium bisulfate, which can clog the instrument. Okay, so other things can be tuned with the parameter, the temperature, but if it is the instrument itself is clogged, then how the sensor will work? how we'll detect the ppm level accuracy. So for that, the typically the temperature will be kept above 220 degree. Yeah. So moving toward the next question, which noise mitigation technique relies on shifting the signal to a higher frequency to avoid the 1 by f flicker, like um, noise region, and using phase sensitive detection? So where we'll use this 1 by f? I think this one you can give nicely the answer. Please. So the correct answer will be here, lock-in detection. Why it is? Run length averaging, uh, Swarovski-Golay filtering, and other isokinetic sampling are not correlating with the 1 by f frequency to noise region, uh, to avoid the noise region. So uh, we can say that the lock-in detection, how it works is, it will only detect in the particular specific region, very narrow region. And the narrow region means it will avoid the asynchronous noises. It will reject using the narrowband filter, and that's how this lock-in detection um, um, is the use for this noise mitigation technique, which avoids the noise region, okay, from the higher frequency. Moving towards the, I think this is last question. uh, Next question, in wavelength modulation spectroscopy, WMS, why is the second harmonic 2f often used for detection instead of the fundamental modulation frequency f? So why we need second harmonic one? First option is the 2f signal is sensitive to the curvature of the absorption line and is largely immune to the baseline slope and intensity fluctuation. Second option is it allows the sensor to ignore the Beard-Lambert law by measuring shape instead of intensity. Third option is the 2f frequency is where the detector's quantum efficiency is naturally at its maximum. And the last option is second harmonic generation doubles the total power reaching the photodiode. What's your answer for this? Johnny, at least answer this last question. After that we'll wind up. John also, please answer the question.
Sir D. The second harmonic generation doubles the total power reaching the photodiode.
D.
Yes.
Okay. Janani, you have any answer? Yeah, John, actually, if you are talking about the second harmonic generation, the power will drastically reduce
Yes.
because collision the absorption, and after that you can say that this is a non-linear process.
Yes.
Yeah, so it's obviously we are not using the second harmonic generation for the power, like doubling the power. So the reason is here option A. Why option A is because the 2f, the second harmonic signal, is sensitive to the curvature of the absorption line
Yes.
and is largely immune to baseline slope and intensity fluctuation. I have discussed about this one. I'll just go through it. Yeah, you can see here how the 2f signal extracted from the absorption profile. You can see
Yes.
here. So the the modulated signal is absorbed, and based on that the extracted 2f signal was detected. What it shows that previously we have seen here that the non-resonant, like dust particle, also fluctuates the intensity, okay, which is one of the main reason for the to use the second harmonic signal. In this region there will be a dust particle also blocking the light, so we need to use the gas, which you can see here, this part where the um, resonance wavelength or intensity is useful. To extract that information we need to use this second harmonic um, detection, okay, to avoid the dust particle and to just focus on the absorbed signal by gas. Okay, did you understood? So it is not doubling the signal, it's just filtering it out properly. So the curvature of absorption line is very sensitive, it is very sensitive to the curvature of absorption line, and also largely immune to the baseline slope intensity fluctuation, okay, and neither it is
Okay.
related to B. It is,
Yes.
yeah, Beer Lambert law, it doesn't matter here for a while, because we are not discussing about the path length or anything else. We are discussing about the wavelength modulation spectroscopy.
Yes.
Okay, and then this also not um, correct, where this detect where it says that where the detector's quantum efficiency is naturally at its maximum. It's not like that. Detector, whatever is detecting, it will be like an absorbed peak only, absorbance peak. That's not correct. Okay. This will be like this something. Okay, but whatever we are getting, whatever we need to do is we need to convert into SHG, like this something. Okay, might be, yeah. So yeah, if you have doubts, let me ask me. This is doubt session. You need to ask so many questions to me. You guys, whatever you are studying, you have any problem with the course, ask me. Okay. You should ask at least 10 to 12 questions per student. You should ask. Anything you have doubts, you just ask. Okay then. If you don't have any doubts, we'll just wind up today's class. Okay, we'll meet next week, and there
Yes.
will be having more and more discussion about the um optics, whatever is used in the gas sensor or gas sensing application. Apart from that, there will be different optical fiber sensors which we'll discuss. Please read and come and have some doubts. So, doubt session also. So, you also can understand properly, and it can also be brainstorming for you for the examination. Have you registered for examination for this course? Okay. Try to register and learn more, and we'll meet next week then. Okay then.